Okay, section 3.4 touches on optimization problems in economics and science. So we're going to take a look at these problems. We're going to take a look at actual real world problems. So in the business world, it's most profitable to minimize costs. And by minimizing the cost, what you're going to do is you're going to maximize your profit, okay? And this goes vice versa. If you maximize your profit, then obviously you're going to minimize costs, okay? But you have control over your costs, okay? And in economics and science, you always have to work within the constraints of the workplace. So profit, cost, and revenue are quantities whose rates of change are measured in terms of the number of units produced or sold. Economic situations usually involve minimizing costs or maximizing profits. Okay, so that's what we're going to see most commonly. So example one, a commuter train carries 200 passengers. So let's put passengers as 2,000 daily from the suburb into a large city. And the cost is $7 per passenger. But research shows that for every 10-cent increase, so plus 10 cents, 40 fewer people are going to ride the train. So minus 40, so it's going to go down 40. Or for every 10-cent decrease, what's going to happen is 40 more people are going to ride the train. So if you take a look at this situation and this situation right here, these are the same. Okay. And now carrying fewer than 1,600 passengers. Sorry, if the capacity of the train is 2,600 and carrying fewer than 1,600 passengers means that the cost exceeds the revenue, so they can't go lower than 1,600 passengers. So we're looking for the domain. Let's call x. X is the number of passengers. Number of people. Okay, we're looking on the domain of 1,600 to 2,600, which is the fewest versus the capacity. What fare should the railway charge to get the largest possible revenue? Okay, a recap from grade 11. What we want to do for the revenue is we have to make a formula so that one bracket or one expression is the number of people or the number of passengers. Okay, and the second one is cost per passenger, cost per person. Okay, so the number of people that ride is usually 2,000, and it is going to go up or down. So let's say down 40x, down per person or per increase. X is going to be the number of increases. Let's call P the number of people. Let's keep it like that. Okay, so it's going to go down 40 people per increase, or yeah, per increased in cost. And then what we have for the cost is it starts at $7, but what's going to happen is it's going to have increase in costs, and then the X represents how many times. So if you had 5 increase in the cost, it'd be 50 cents, in other words. Okay, so if we take a look at this domain right here, so this is the domain. Domain of P, domain of number of passengers. Since the number of passengers must be at least 1,600, we know this number of people, this expression right here, 2,000 minus 40x, must be greater than or equal to the 1,600. Okay, so if we simply bring this over and bring this over, we're left with 2,000 minus 1,600 equal, or has to be greater than or equal to 40x. So 400 is greater than 40x. 40, 40. Okay, so 10 is greater than or equal to x. And again, x is the number of increases. So since the number of passengers cannot exceed 2,600, we also have to limit x. So we know that our 2,000 minus 40x has to be less than or equal to 2,600. Okay, bring that over, bring that over. We have 2,000 minus 2600 is less than or equal to 40x. I get minus 600 is less than or equal to 40x. Divide that out. Okay, negative 600 divided by 40, negative 15. Okay, so what this means is the actual domain of x. So we have the domain of p, we have the domain of the people. And what we did is we took this 2000 minus 40x and we subbed it in right here. Then we evaluated when it has to be greater than 1600 and less than 2600. So our actual domain for the number of increases is between negative 15 and 10. That's our actual domain for the number of increases in price. Okay, all I did was rewrite the revenue formula. So if we expanded the revenue formula, what we actually get is negative 4x squared minus 80x plus 14,000. And I'll let you expand that by yourself. So what we're going to look at, and we're going to stick to only looking at increments of 10 cents. What we're going to look at is when the revenue is at a maximum or a minimum. So negative 8x minus 80. Okay, so we're going to take a look when negative 8x minus 80 equals 0. Bring that over. 8x equals negative 80. Divide both sides by 8. We get x equals negative 10. Okay, this negative 10 is in this domain, so we can check it. Now what we have to do is we have to check the revenue at negative 15. We have to check the revenue at negative 10. And we have to check the revenue at 10. So both endpoint, EP, endpoint, and this is going to be either a max or a min. Not necessarily. This is going to be like a turn. Okay, that negative 10. So at negative 15, if you sub in the negative 15 to the original, you'll get 14,300. If you sub in the negative 10 to the original, you're going to get 14,400. Okay, and if you sub in 10 into the original, you're going to get 12,800. So which one is the greatest revenue? I get when R equals negative 10. Okay, therefore, in order to maximize revenue, we must have negative 10 increases, which all that means, negative 10 increases of 10 cents. Okay, what this means is we take the negative 10, we multiply by 10 cents, and we get negative $1. Okay, so it's actually a decrease of $1. So the fare should be, well, our original fare was 7, subtract the 1, $6 for a revenue of $14,400. And the number of passengers. So what I'm just doing right here is like this expression here is for 2000 minus 40x is for the number of people. And then this is going to be like the cost. That's why I did 7 minus 1. Okay, so the number of passengers is going to be the 2000 minus 40 times negative 10. So it's 2000 plus 400. Okay, so the fare should be $6 for a revenue of 14,400 with 2,400 passengers.